If you grow anything in a greenhouse during the summer, you know how brutal it can get. Once the temperature climbs past 100 degrees inside, plants start showing stress fast. In my case, the tomatoes were suffering the most. Flowers were falling off before they could turn into fruit, leaves were curling, and growth had basically stalled. I was already running 2 large exhaust fans almost 24 hours a day, and it still wasn't enough on the hottest days. I didn't want to keep throwing more electricity at the problem. I wanted a smarter solution, something that could actually cool the air instead of just moving hot air around. That's when I started researching evaporative cooling. The concept is simple but powerful. When water evaporates, it absorbs heat from the surrounding air. Big commercial greenhouses have used wet walls for years, but those systems are expensive and still need constant electricity. I decided to build my own version with 3 important upgrades. First, I would use a waterfall-style cooling wall instead of a flat pad. Second, I would make the whole system automatic so it turns on and off by itself based on temperature. And third, this was the part I was most excited about. I wanted it to run completely on solar power so I wouldn't be adding to my electricity bill. The idea was pretty straightforward. I would build a wall on one side of the greenhouse with a mesh panel. A small pump would push water up to the top, letting it flow down and create a constant curtain of water. Exhaust fans would then pull hot air from outside through that wet curtain. As the air passes through the water, evaporation cools it down before it enters the growing space. To make it automatic, I added a simple temperature sensor and a relay. When the temperature inside the greenhouse gets too high, the relay turns on the pump and fans. When it cools down enough, everything turns off again. And because I used a solar panel, charge controller, and a small battery, the system can run even on cloudy days or at night using stored power. I kept the electronics as simple as possible on purpose. I used a waterproof temperature sensor and a basic relay module. You don't need advanced programming skills for this. I'll show you the exact wiring later so even beginners can follow along. Before I started building, I laid out all the main parts I would need. For the cooling wall, I used a submersible pump, PVC pipes and fittings, a large plastic bin as the water reservoir, and a piece of evaporative cooling mesh. For the solar side, I chose a 100-watt solar panel, a small charge controller, and a 12V battery. The automation part only required the temperature sensor and relay. In total, I spent around $175 on everything. One thing I want to be clear about from the beginning is safety. Mixing water and electricity always requires caution. I made sure to use proper waterproof connections, a GFCI outlet where needed, and I protected all the low-voltage wiring. I'll show you exactly how I handled this safely throughout the build. At this point, I had a clear plan and all the parts ready. The first big step was building the physical waterfall wall and setting up the solar power system. After that, I would add the temperature sensor and relay to bring the automation to life. I was excited to get started, but I also knew there would be some trial and error along the way, and there definitely was. But before we dive into the build, let me show you what my greenhouse looked like on a normal hot summer day before I made any changes. With the plan in place and all the parts ready, it was time to start building. I decided to tackle the physical cooling wall and the solar power setup first. This way, I could get the mechanical side working before adding the automation electronics. I started by building the frame for the cooling wall using some leftover pressure-treated 2x4s. I made a simple rectangular frame about 4 feet wide and 6 feet tall, then attached it securely to the side of the greenhouse. After that, I installed the evaporative cooling mesh inside the frame and made sure it was tight, and even so, water would flow smoothly across the entire surface. For the water system, I placed a large plastic bin at the bottom as the reservoir and installed a submersible pump rated around 450 gallons per hour. I ran PVC pipe from the pump up to the top of the frame and used a perforated pipe to spread water evenly across the mesh. The water flows down through the mesh, collects at the bottom, and returns to the reservoir in a closed loop. Now, let's talk about the solar power setup, because this is where I had to do some calculations to make sure everything would work reliably. I estimated that when the system is running, the pump would use about 45 to 50 watts, and the 2 exhaust fans would use around 60 to 70 watts combined. That brings the total load to roughly 110 to 120 watts when everything is on. Assuming the system would run about 6 hours per day during the hottest part of summer, I calculated that I would need around 720 watt-hours of energy daily. Adding about 25% for system losses, I needed the solar panels to provide approximately 900 watt-hours per day. With an average of about 5 peak sun hours in my area during summer, I determined that I needed at least 180 watts of solar power. To give myself some headroom for cloudy days and future expansion, I decided to go with a 200-watt solar panel. This size gives me a good balance between performance, cost, and reliability. For the charge controller, I chose a 30-amp MPPT controller instead of a cheaper PWM model. MPPT controllers are more efficient, especially when sunlight conditions change throughout the day. They can extract more power from the panel compared to PWM, which is important if I want the system to perform well even on partially cloudy days. The 30-amp rating gives me plenty of capacity for the 200-watt panel and leaves room if I decide to add more solar later. I mounted the 200-watt panel on the roof of the greenhouse facing south with a slight tilt to maximize sun exposure. From the panel, I ran the wires down to the MPPT charge controller mounted on the inside wall. I then connected a 12V60Ah battery to the controller to store energy for when the sun isn't shining directly. The charge controller also has a load output, which I plan to use later to connect the pump and fans through the relay. One important thing I learned while setting this up is that panel angle and positioning really matter. I had to adjust the tilt a couple of times after checking the output at different times of the day. If you're building something similar, I recommend testing your panel's performance before permanently fixing the mount. By the end of this stage, the physical cooling wall was complete with water flowing nicely through the mesh, and the solar power system was fully installed and ready to provide clean energy to the project. Everything on the mechanical and power generation side was working as planned. Before moving on to the electronics and automation, I let the water system run for about an hour to check for leaks and make sure the mesh stayed evenly wet. I also took some temperature readings of the air passing through the wet wall and could already feel cooler air coming through. This gave me confidence that the evaporative cooling concept was going to work well once I added the automation. Now that the physical cooling wall and solar power system were in place, it was time to add the most important part, the automation. This is what would make the whole system turn on and off by itself without me having to babysit it every day. The brain of the system is actually quite simple. I used a waterproof temperature sensor and a relay module. The sensor constantly reads the temperature inside the greenhouse. When the temperature rises above a certain threshold that I set, the relay closes the circuit and turns on the pump and the exhaust fans. Once the temperature drops back down to a comfortable level, the relay opens and everything turns off again. I chose a DS18B20 waterproof temperature sensor because it's accurate, cheap, and easy to work with. For the relay, I used a common 12V single-channel relay module that can handle the current from the pump and fans. Everything runs on 12 volts from the solar system, which keeps things safer around water. I mounted the temperature sensor inside the greenhouse at about the height of the plants so it would read the actual temperature the plants were experiencing, not the temperature near the ceiling. I then ran the wire from the sensor to the relay module, which I mounted on a small board near the battery and charge controller for easy access. Wiring was straightforward, but I had to be careful. I connected the positive and negative from the solar system's load side to the relay's input. Then I connected the pump and fans to the relay's output. The key is making sure the relay is rated high enough to handle the combined current of the pump and fans. I also added a fuse on the positive line for extra protection. Here's where things got interesting. When I first tested the system, nothing happened. The relay wasn't clicking, and the pump and fan stayed off, even though the temperature inside was already over 100 degrees. I spent almost an hour checking connections and rereading the wiring diagram before I realized what I had done wrong. I had wired the relay backwards. The control signal from the temperature sensor was connected to the wrong pins. Once I swapped the wires around and double-checked everything, the relay finally clicked when the temperature reached my set point. It was such a simple mistake, but it taught me to always test the relay separately before connecting the high-current devices. After fixing the wiring, I tested the system again. This time, when the temperature climbed above 95 degrees, the relay clicked on. the pump started pushing water through the mesh, and the fans turned on to pull air through the wet curtain. About 30 minutes later, when the temperature dropped below 88 degrees, everything automatically turned off. It was exactly what I wanted. I also tested how the system behaved on a partly cloudy day. Even though the solar panel wasn't getting full sun the whole time, the battery had enough stored power to keep everything running without any issues. This gave me confidence that the system would work reliably in real conditions. One thing I want to mention is safety. Because this system involves both water and electricity, I made sure all connections were properly waterproofed and used heat shrink tubing and electrical tape generously. I also labeled all the wires so it would be easy to troubleshoot later if needed. At this point, the automation was working correctly. The system could now decide on its own when to turn on and off based on temperature. This was a big milestone because it meant I wouldn't have to manually switch anything on hot days. In the next chapter, I'll show you the real test how much the temperature actually dropped once the automated solar-powered cooling wall was running at full capacity. After everything was built and the automation was working properly, it was finally time to see how well the system actually performed. I waited for a hot, sunny day to run a proper test. On the day of the test, the temperature inside the greenhouse reached 108 degrees Fahrenheit around 1:30 inches the afternoon. This was before I turned on the cooling system. I let the automated solar-powered waterfall wall take over. The temperature sensor triggered the relay. The pump started pushing water through the mesh, and the fans pulled air through the wet curtain. Within the first 30 minutes, the temperature inside the greenhouse had already dropped to 94 degrees. After about an hour and a half, it stabilized around 84 to 86 degrees Fahrenheit, even though it was still hot outside. That's more than a 20-degree drop, and the system was running completely on solar power with no electricity from the grid. I was honestly surprised by how effective it was. The air coming through the cooling wall felt noticeably cooler and fresher. My tomato plants, which had been looking stressed, seemed to perk up over the next couple of days. The flowers stopped dropping as much, and new growth started appearing again. On the solar side, the 200-watt panel performed well. On a full sunny day, it easily kept the battery charged while powering the pump and fans for about 6 to 7 hours. Even on a partly cloudy day, the battery had enough reserve to keep the system running without shutting down. I was happy with this performance. Of course, there are some things to consider. The system does increase humidity inside the greenhouse because of the evaporating water. In my case, humidity rose from around 45% to about 75%. For some plants, this is fine, but if you're growing things that prefer drier air, you might need to improve ventilation or run the system for shorter periods. Also, the mesh needs occasional cleaning to prevent algae buildup, and the water reservoir should be checked regularly. Another lesson I learned is the importance of proper sensor placement. At first, I had the temperature sensor too close to the cooling wall, so it was reading cooler air than the rest of the greenhouse. Moving it to the middle of the growing area gave much more accurate readings and better automation performance. Overall, I'm very satisfied with how this project turned out. Building a solar-powered automated cooling wall was more effective and easier than I expected. The combination of evaporative cooling, simple automation, and solar power created a system that actually solves a real problem without increasing my electricity bill. If you've been struggling with high temperatures in your greenhouse, I think this is a project worth considering. You don't need advanced electronic skills, and most of the parts are easy to find. Just take your time with the wiring and safety, and you should be able to build something similar. Thanks for watching this build. If you have any questions about the parts I used or how I wired everything, feel free to leave a comment below. I'll do my best to answer. And if you end up building something like this, I'd love to hear how it works for you. See you in the next video.